Okay. So, we are doing folding. Today, I will be considering retiming for folding. Okay. We know that this formula df u comma v was W n plus schedule v minus schedule u minus p u. What was the context? In the DFG there is a node u, just a minute, W number of delays, okay. P u is the number of pipeline latches in node u. These are all known, so I am just briefly recalling. W is the original number of delays, okay. Folding factor was n, that is n nodes of the type u are mapped to one single hardware unit of type HU, and that is pipelined by pu number of delays. Small u is the schedule of particular node capital U, small v is the schedule of particular node small v, capital V. Then this particular edge is implemented in the hardware, where one side is one hardware unit of HU type, another side is HV type. So, the delay between HU and HV will be this much. This is what we derived and we used in one of the folded circuits earlier. Okay. Assuming that schedule, that hardware unit V works for the node V at a schedule V, and hardware unit HU works for the node U at a schedule U. Okay. We have got NL for the nth word input word, we have got NL plus u, u could be 0, 1 up to n minus 1. So, when it is NL plus u, hardware unit HU works for node u. Similarly, when it is NL plus V, hardware unit HV works for node V, and the delay in between them should be this much. So, this is what I did. But here the problem is there are minus signs, and as I told you that time that there is a possibility that sometimes because of your choice of V u, P u, and also because of the values you have for W and N, this could be negative. One way to get out of the negativity is to first retime the DFG by assigning retiming values to various nodes and then do this folding. So, suppose I do retiming of this. So, I use R of u as a retiming value for node u, R of v as a retiming value for node v. Then after retiming, we have got the delay changes from W to W plus R of V minus R of U. Of course, you should choose this so that feasibility is satisfied, feasibility inequality, that is W plus R of V minus R of U, that should be greater than or equal to 0. Alright, that should be greater than or equal to 0. W plus R of V minus R of U. That is one set. So, that you have studied in the case of retiming, that you assign retiming values so that this inequality is satisfied. So, nobody after retiming turns out to be negative. Alright. But now, if I fold it, that is after the delay is changed from W to this much, if I now fold it, here in the formula only W will be changed to this value, other figures do not change, they remain same. So, if I call it df R superscript R for retiming, that is after retiming, then this delay expression will be W plus R of V minus R of U, this is the new delay, that times n plus remaining things are as before, V minus U minus P U. And now I want this to be always positive, not negative. This I can ensure by choosing R V, R U, these are my handles. I can choose them. So, even if my schedules are, we are giving rise to negative value here, now they will not. How? Because if you simplify it, you take W into N plus V minus U minus P U, which is same as original DF U comma V. So, this is equal to df u to v plus remaining portion is rv minus ru times n, all right, rv minus ru times n, and this should be greater than equal to 0. So, if you take rv minus ru n on the other side, this gives rise to another inequality ru minus rv into n less than equal to, into n I take it to this side, df u to v, that is originally before retiming whatever be the expression, that you divide by n. Now, ru is integer, rv is integer, so difference must be integer. So, I will take the integer value of this division, that is if you divide, take the quotient, okay, that is called floor. So, ru minus rv, this should be less than equal to this. So, this is another set of inequality involving ru and rv apart from this. Other one was feasibility equality, and now we have got another set of inequalities. So, you have got a larger set of inequalities now. If you solve them, you get appropriate values of ru, rv which you can use, so that both feasibility is satisfied and none of the delay after folding like this turns out to be negative, because that is how this inequality has been obtained. All right, I take an example now. Take another filter, IIR filter, and this is the conventional IIR filter you are familiar with. Okay. 1, this is 2, 3, 4, 5, 6, 7, 8. Okay. This is a conventional digital filter. All of us know direct from 2 digital filter. Okay. Pipeline latches PA equal to 1 as before, multiplier requires 2 latches. Okay. N is 4, that is 4 adders to be replaced by 1 hardware adder unit, and 4 multipliers to be replaced by 1 hardware multiplier unit, very much like the example 1 which we considered earlier. And schedules also are same as which we considered last time. Is A folding set for adder four, 2, 3, 1, is B, sorry, is multiplier, I am sorry, is M Okay. Now, like the previous example, we calculate the delays after folding. So, 1 to 5 df 1 to 5 will be 1 delay between 1 to 5. So, 4 into 1 plus V the destination is node 5. Okay. Or maybe I start with 1 to 2, that is better. Let us start with 1 to 2. Adder to adder, then we will consider adder to multiply. 1 to 2. No delay in this edge, so 4 into 0. Plus V, that is the schedule of node 2. Schedule of node 2 is 0, 1, 2, 3, that is 1, minus schedule of node 1, node 1 is 3, so 3, minus pipeline latch for adder which is 1. Okay. So, this is negative. So, first one is turning out to be negative. minus 3. We want every edge delay to be positive, but here I am getting negative minus 3. Fine, fair enough, let us still proceed. Then 1 to 5. Here I have got 1 delay, so 4 into 1 plus 5 means schedule 0. This part remains same because that relates to adder 1. So, its schedule and number of pipeline latches do not change. So, minus 3 minus 1, which is 0, no problem. Okay. Then DF 1 to 6, DF 1 to 6, again 1 delay. So, 4 into 1, 6 has a schedule 2, this part remains as before because it is adder 1. So, 4 and 2 6, 3, so this is 2, 1 to 6 is 2. Then DF 1 to 7, two delays. So, 4 into 2 plus schedule of 7, which is 3, minus this part remains same. So, this is 7, positive, no problem. Then DF 1 to 8, 1 to 8 also, 2 delays, 4 into 2, schedule of 8 is 1, this part remains as before, so it is 5. So, I am done with 1, so DF 3 to 1, no delay. So, 4 into 0, 1 has a schedule 3, minus 3, 3 has a schedule 2, and 3 also is an adder. So, pipeline latch is 1. So, this is 0, no problem. Then DF 4 to 2, that is I am still considering adder to adder, no delay. So, 4 into 0 plus 2, adder 2 has schedule 1, minus 4, schedule of 4, schedule of 4 is 0, and still adder. So, pipeline latch is 1, so it is again 0. Okay. Then comes the other one, multipliers, 5 to 3, 5 to 3 I am directly working out, 5 no delay. So, 4 into 0 plus 3 is a destination, it has a schedule 2, minus 5 is a source schedule 0. So, 2 minus 0 2 minus the number of pipe latches for multiplier, which is 2, PM is 2. So, 2 minus 2, which is 2 minus 2, which is 0. Similarly, DF 6 to 4, DF 6 to 4, 4 is the destination, which is an adder, schedule 0, 6 schedule 2, and no delay in the spot. So, 0 minus 2 minus number of pipeline latches in multiplier 6, which is 2. So, again I am getting a minus quantity. Then DF 7 to 3, 4 into 0 plus 3 has a schedule 2, minus schedule of 7 is 3, minus 2, because pipeline latch is 2 here. So, again I am getting a negative quantity, minus 3. No delay. So, 4 into 0 plus schedule of 4, schedule of adder 4 is 0. So, 0 minus schedule of 8 here is 1. So, minus 1, and again multiplier is the source. So, its number of pipeline latch is 2. So, minus 3. So, these are the things, this fellow, this fellow, this fellow, and here one fellow. They are the troublemakers, they are negative. So, I will be retiming, that is I will be assigning retiming values R of 1 to node 1, R of 2 to node 2, R of 3 to node 3, like that. Okay. And then I will get some inequalities, and in addition to the feasibility inequalities. What are the new inequalities? We have already seen the formula, Ru minus Rv. So, if you consider 1 to 2, this will give rise to R of 1 minus R of 2, R of 1 minus R of 2, u to v, R of u minus R of v. This should be less than equal to original df divided by capital H, that is 4, and its there is minus 3 by 4 its quotient. Minus 3 by 4, you have to go to the integer which is just below this. So, minus 3 by 4, the integer below this is minus 1, because it should be less than equal to minus 3 by 4. Ideally, it should be less than equal to minus 3 by 4. But R1 is integer, R2 is integer, difference is integer. So, if the integer is to be less than equal to minus 3 by 4, so it has to be less than equal to minus 1, okay, because minus 3 by 4 is not an integer. So, therefore, you can write it this way, minus 1, sorry. Similarly, R1 minus R5, R of 1 minus R of 5, this will be less than equal to 0 by 4 and the integer below that less than equal to. So, 0 by 4 integer itself is 0, which is itself is an integer which is 0. So, no need to go below it because it is not a fraction. So, this is another inequality. Then R1 minus R6 less than equal to 2 by 4, that is 1 by 2, you have to go one step below the next integer immediately below 1 by 2, that is 0. Okay, 2 by 4, that is half. So, R1 minus R6 should be less than equal to half. But this integer, difference is an integer. So, integer must be less than equal to half, means it must be less than equal to 0. Because this side is integer, right side has to be integer. That is why we are taking the floor. There is the next integer on the lower side. Okay. Then R of 1 minus R of 7 less than equal to 7 by 4. 7 by 4 is 1 plus 3 by 4. So, integer just below this is 1. So, 1. Similarly, R of 1 minus R of 8 less than equal to 5 by 4, which is 1 plus 1 by 4, integer below it is 1. R of 3 less than equal to 0. R of 4 0, all right. And on this side, R of 5 minus R of 3 less than equal to 0, of course, 0 by 4, which is integer 0. So, it remains 0 here. Then R of 6 minus R of 4 less than equal to minus 4 by 4, which is minus 1, but that is an integer, no need to go below that. So, minus 1. Then R of 7 minus R of 3 less than equal to minus 3 by 4, which is minus 3 by 4 is a fraction. So, integer below that is minus 1. So, minus 1, and same here, R of 8 minus R of 4, here also minus 3, so it will be minus 1. So, you get a set of inequalities and you have got the feasibility inequalities. Feasibility inequalities were simple. For instance, between 1 and 2, you should have original W, which is 0, plus R of 2. So, 0 plus R of 2 minus R of 1, that should be greater than equal to 0. So, between 3 and 1, 0 delay, plus R of 1, there is the destination, minus R of 3 greater than equal to 0, so on and so forth, 1 to 5. 1 to 5 is 0 plus, not 0, here is 1 delay. So, 1 plus r of 5 minus r of 1 greater than or equal to 0 dot 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 dot. We know how to do that. So, you have a set of inequalities called feasibility inequalities which come from retiming, and then you have got a set of inequalities which come from folding consideration. So, you have got a larger set of inequalities, hoping that this has a solution space. If you give it to a computer package, it can give you solution sets, and using any such solution set you can retime it. Okay, the delays will be distributed changed now. Okay, because if you have R1 some value and R5 some value, so this will get changed to 1 plus R of 5 minus R of 1 and like that. Okay, so you change the delays, you will be coming out of this negative problem. This is a general way of doing, but a practical way of doing applicable to DSP circuits is often obtained by cut set retiming. Let me explain that. Now, consider this, I have got these 4 fellows who are creating the trouble, they are negative. Now, you understand that if any edge I increase the delay by 1, so if it was originally W, then in the folded figure you have got Wn factor coming, right. If W goes up in any edge by 1, W plus 1, so it becomes W plus 1 into N, so delay increases by N. You understand what I am talking of? In that folded delay formula df, we have Wn plus small v minus mu minus pu. If W is increased original edge by just 1 delay, in this formula it increases by capital N, right. So, therefore, consider 1 to 2, 1 to 2 there is no delay. The edge is like this is one edge, this is 1 to 2 direct edge. If in this edge I now introduce suppose 1 delay by hook or crook, then instead of 4 into 0, it will be 4 into 0 plus 1. So, 4 factor or additional 4 will be added. So, 4 minus 3 it will be plus 1. Similarly, here also minus 4, 6 to 4, there is no delay. If I can introduce the delay here, like here, if I can introduce the delay here, okay, if I can introduce the delay here, then what happens? Earlier I had 0, now it will be that is 0 means 4 into 0, now it is 4 into 0 plus 1, if I have a delay 1 here, remaining things are same. So, a plus 4 factor like a plus n factor, plus 4 factor would come up here, that will get added with minus 4, it will become 0, okay, it will become 0, this will become 1. So, 7 to 3 minus 3. So, 7 to 3 if here I have one delay, then in this calculation instead of 4 into 0 it would be 4 into 0 plus 1, that is 4 into 1. So, 4 factor would get added with minus 3, so it will become plus 1. And last one 8 to 4 again no delay, if I have a delay here then a 4 will get added, 4 minus 3 it will become plus 1. Okay. But I cannot arbitrarily add delays, but if I add delays that amount to cut set retiming, I am done, because cut set retiming is a valid retiming. Now, you see the mark, I want a delay here, delay here, delay here. Clearly, if I just remove these edges, this one, they form a cut set, because the circuit is divided into one side this way, adder 2, adder 4 at this edge and remaining part here, right. So, they form a valid cut set and all are in the forward direction, left to right, left to right. So, I can happily add a delay here. So, I can put a delay here. So, fine. So, here I just added delay from outside, there was no delay, they are not present here, but it is forward path pipelining, forward path retiming, I just added delay, they form a cut set, these 3 edges, if you cut them, the entire DFG is cut into 2. So, for a valid cut set only one direction. So, I happily add a constant number of delay, one delay in all of them. So, this becomes positive, minus 4 to it becomes 0, from minus 3 it becomes 1, from minus 3 it becomes 1. But other problems are this side 7 to 3, sorry not here, I am very sorry, not here, 1 to 2. Okay, these 3, 1 to 2, 1 to 2, 6 to 4, 8 to 4. But now I am left with 7 to 3, that is another direction. That is in a loop. Like if you go through this way, the node 1, then this 2 delay, then node 7, then node 3 and back. In a loop, I cannot bring in delay, new delay from outside. That violates retiming, as you have told. So, we have to use existing delays of the loop for doing retiming. I cannot, like unlike here, where these delays were not at all existing, I brought in from outside world. Here I cannot do that, but I must have a delay here. So, what I can do is this. This is one edge, you can view it this way. Maybe you can just put a dummy node here, dummy, which is just accepting this and splitting it in various direction. Through this dummy node, there is one delay going in this direction and another delay going in this direction, because this delay was common. I have just split. Now, see what edges I am cutting. I am cutting this edge and this edge. So, they form a valid cut set, because if I remove this and this node is a singleton left out and remaining part of the circuit another part. So, the entire DFG or circuit is cut into exactly 2 mutually separate DFGs. One is the single node 7, other is the remaining part of the DFG. But one is incoming direction, that is edge is coming from other half of the DFG to node 7, another is going out of node 7 to the other part of DFG, right. In one incoming edge there is a delay, this I can cut, so I can bring back the delay on this side. In one direction I remove and add the same delay in the other direction, that is the formula. Okay. Now, you can merge the two lines, take the delay here, okay, this part from delay has taken out, and here the other edge which has delay, that delay I am putting here. This is the circuit we considered the other day, but only thing you should check is this: in the forward path pipelining there was no problem, I brought in extra delay, but in the loop wherever I moved a delay, earlier there was a delay here, here I moved it here. So, in this movement, because some delay which was existing already in the part of the in one of the edges that have moved to some other edge. So, maybe one of the edges now getting less delay, like this edge, you can remove this dummy node now. This edge earlier had 2 delays, which edge? 1 to 7. 1 to 8 earlier had 2 delays, now also 2 delays, no problem. But 1 to 7 I had one delay here. So, 1 to 7 had 2 delays. One of them now has moved up. So, 1 to 7, here one delay has come down, which means from DF 1 to 7, whatever is the value, 4 will get subtracted. Earlier I had 4 into 2, like here 4 into 2, now it will be 4 into 1. So, 4 will be subtracted. Question needs to be checked is this: does it lead to new negative edge? Here fortunately not, because it will be now 7 minus 4, which is still positive 3. But if it so happens that after you subtract 4 from the original value you get negative, then you cannot do anything. Okay, so this needs to be checked after you complete retiming and all. You have to check wherever delay has moved from one edge to another edge. So, some edge is getting extra delay, some edge is getting less delay than earlier. Whichever edge loses some delay, you have to recheck whether the the due value of this folded delay, is it still positive or is negative? If positive, you are done. All right. This is a practical way of doing folding, with retiming, that is using cut set. But remember, you have to do this cross checking at the end also. So, that is all for this up. Thank you very much.